last lecture we did some example on the lecture, and today we will do this example on the Kale and also Proteus. How can we implement the same example with the Kale? How can we check it? And how can we complement it in the Proteus? In here we have the first question. We have a conveyor system and we need to do send a positive pulse from the port 2.0 when the 1,000 boxes pass the conveyor. Okay, this is the question, and sensor is connected to the port 3.4. As I said on last lecture, it is so important for us. Why? In this question, we will use counter mode, and this value is important for us. Why? We cannot select randomly. We have some reserved pins for the counters. Maybe we can remember. Yes, here we have block diagram for TC0 and TC1. This is the reserved counter pin and reserved counter pin. And as you see here, port 3.4 means we can use this pin as counter for the TC0. Okay, so we will do this question on the K now. Okay, I will copy the related program codes because we explained before. Maybe we can check it again together. Here we have program codes. Please let me arrange the program codes to explain easily. Okay, for the solving, we will use another vector address. This is 0b hex for the TC0, and T mode setting is for the 16-bit mode, and counter is selected. DPTR, this is the initial value for us. Actually, here we have an important issue. When 1,000 boxes passes from the conveyor, what will we have for the counting register? What do you think? The counting register value is 6, 5, 5, 3, and 5. So there is no overflow, right? TF0 is 0. So the exact value for the initial value for this question should be, of course, 6. Okay, 6. But it is not so important for the for this lecture because the numbers are so high generally, so 1 is meaningless for us. Okay, but the exact application you have to consider it. Okay, let's continue now. The initial values are loaded. Enable timer 0, enable all. Set bit TR 0, TC0 is enabled, and clear port 2.0 because we'll use this pin, and we have an endless loop here. Program will remain here. Let's compile it and let's check it on the debug session. But To check this program on the debug session, we have to use 1,000 click. So we can use a lesser number for this question. Okay. For example, we can use 6, 5, 5, 3 and 4, for example. What is mean now? When two boxes passes from the conveyor, we will send a positive pulse from the port 2.0. Okay. Okay, let's try it now. We have no error and no warning. Let's go to the debug session part. Yes, for this question we need some peripheral units. Which one? Let's check it. Here we have an interrupt tab. Let's use it. Interrupt. Port 2.0, so we need to port 2. Where is it? Port 2. And also we need timer. Let's get timer 0 because we use timer 0. Okay, this is the initial values for the interrupt, port, and TC0. Let's start the program. We are in sjump start and program will continue from line 5. Here, when we apply this code here, the settings will be changed 16-bit timer mode. 16-bit counter mode. Yes, here as you see 16-bit and counter. And we have initial values. When we load it, as you see here, the counting register will change. Enable timer 0 here. Okay, we are in line 9. Enable timer 0. When we apply this program code, timer 0 is here in the interrupt tab. It will be enabled. Okay, it's mean enabled. As you see, timer 0 is enabled and set bit enable all. This pin will be enabled. And set bit TR0 here. We have a section here. Set bit TR0. We have to clear port 2.0 because what is the result for us for this question? Sent a positive pulse from the port 2.0 and the initial value of the port 2.0 is already 1. Because of this, we have to clear it. And we are in endless loop. Now we need to wait. Some boxes will passes from the conveyor. How? We have to use, of course, port 3 for this solving. As you remember, port 3.4 is the counting pin for us. Which one? 0, 1, 2, 3, and 4. When we click one time, as you see here, the counting register or the TL0 will change from FE to FF. Okay, it's mean one product, one box will pass from the conveyor. Let's continue. When we continue, we are in again endless loop because we need to wait another box and we can do it. As you see, TH0 is 00 and TL0 is 00 and TF0 is set. Okay, the program will behave as from line 13 to line 4. Why? In the interrupt structure, we have a interrupt source, all settings will already done. So we need to go related vector address, and in this vector address the program will tends to the counter 0. So we have to go line 4. Let's check it. Yes, as you see here, we are in line 4, and we will go to the counter 0 subprogram, interrupt subprogram. Yes, here port 2.0 will set and clear, and we need to load initial value to the counting register again and return interrupt. We will exit the interrupt subprogram, and as you see here, we are in line 13 again, which is endless loop. We can check it, this kind of question as like that. The passing boxes will simulate with a button, as you see here, and port 2.0 will send a positive pulse. We can implement it by a LED. Okay, let's load the related machine codes and let's try it. Yes, program start to the work and clear the related LED. Let's try a box, and when we try another box, LED will light on and off. Okay, but maybe we can't see. Yes, as you see here, we can't see. Why? What do you think? What is the reason? Maybe I can show you program codes. It is the program codes. Yes, here, as you see here, line 14 and 15, set bit port 2.0 and then clear port 2.0. That's processed in microseconds. How can we see it? Okay, if you want to see it, we can use a delay, maybe by using a nested loop. Let's try it. Move 10 hex 255 decimal, move 11 hex 255 decimal, and in this part DJ and Z 10 hex, wait. Of course, in this line, and then we have to load initial values for 10 hex address, and then DJ and Z 11 hex, wait again. And after this command, we have to load initial value because the program will not go back to the start label, right? When we go enter to the interrupt subprogram, we cannot go to the main program again. Program will go back to the line 15. So we cannot load the initial values of 11 if you don't write here. Okay, we have a nested loop here, and then for the delay, of course, and then we will clear the related pin. Let's check it. We have no error and no warning, and we can try directly on the Proteus model. Let's try it. Program is started to work. One boxes go and another box. Yes, as you see here, we can see as a flicker. Okay, flicker, light on and off, light on and off. Let's continue with another example. Another example is that we want a signal from port 2.0 as like that. It's a square wave as you see, and the frequency is 2 milliseconds. So we need to do logic 1 for a 1 millisecond and then logic 0 for another 1 millisecond. That's all. So we need to use timer, of course. Here we have the solution. For the 1 millisecond, we need to do 833 machine cycle. Let's try these program codes. Yes, let me arrange it. Here we have to use AND directive, and also here we don't have command move. Okay, let's try to build it. Yes, we have no error, no warning. Yes, the first of all, we used the same vector address because again we use timer 0. Maybe we can change it. Yes, we can change it for this question. What is the vector address for the timer 1? 1B hex. Let's try it. Try to use it. 1B hex, timer 1 label. T mode will be 1 for 16-bit mode and 0 for timer 0. And we have to use TH1 and TL1 and TR1. Enable timer 1, of course, and here 1 and 1. I guess it's finished. Yes, we have no error and no warning. Let's try it now. Maybe we can try on debug session again. And we need some peripheral units. Which one? Interrupt, timer 1, and port 2.0 as I remember. Yes, port 2. Let's try now. We are in line 2 and T mode will be done for the timer 1. Now 16-bit mode timer. Yes, 16-bit timer. This is the initial value for the 1 millisecond and enable timer 1. As you see here, timer 1 is enabled. Enable all and set with TR1. Now we are in line 12 for a 1 millisecond. Okay, maybe we can try to go 13. Yes, when we go to the 13, as you see here, second will be 1 millisecond. This is the first time for us, and port 2.0 will be complemented, and the initial value will be load to the counting register and return interrupt. We are in here again. Yes, 2 milliseconds, 3 milliseconds, 4 milliseconds, and it will continue as like that. Okay, maybe we can try it continuously. As you see here, port 2.0 is 0 and 1. Okay, this is the trying on debug session part. Okay, maybe we can try also Proteus. So yes, here. I remember it will ready for the. Yes, here it is ready for us. Port 2.0, we have an oscilloscope. Maybe we can close. Yes. Okay. Let's load the related program codes. This is not the same one. Yes, here. Okay. Where is the oscilloscope? As you see here, we have a square wave. Maybe we can check the time. We use 0.2 millisecond for the time division. 1, 2, 3, 4, and 5. 5 square, it means 0.2 times with 5, 1 millisecond. Logic 1 and 0, 1, 2, 3, 4, 5, 1 milliseconds for logic 0. Okay, we have another question here. We solved this question with another way, but here we can solve this question by using this program code. Maybe I can explain for you because this is good answer, I think. Here we have another question. Let's remember the question. Here we have a sensor again, and it is connected to the port 3.3. They are classified according to the box length. Its mean transit time in a conveyor system with constant bell speed. If the box size 50 millisecond and under this value, it is classified as A. Okay, when this condition is occurred, we will send a positive pulse from port 2.0. Otherwise, it is classified as class B. Okay, over the 50 milliseconds, classified as 50 milliseconds. Sorry, classified as B. And on this condition, we will send a positive pulse from port 2.1. Perform the necessary assembly program using interrupt structure. For 50 milliseconds, it is wrong. 50 milliseconds, we need to do that machine cycle 41667. So the counting value should be compared this number, and we can decide to the box length. Let's examine this program code now. This vector address belongs to the external one, y. Here, as you see, it is connected to the port 3.3, and when you check, yes, when you check port 3.3, as you see here, we have to use external interrupt. On this interrupt structure, we have to decide IT1. Why? Uh, Interrupt can be occurred on the logic 0 from this pin or falling edge transition. For this question, we need, of course, falling edge transition. Yes, falling edge transition. Why? Because as you see, when the boxes from here, falling edge transition will occur. Okay, so we can easily understand this. Box is passed from the conveyor or under the sensor. Let's continue to the solving now. So we need to do, we need to use interrupt 1. This is the T mode settings for what? Gate 1 is 1 because is there an option to use interrupt structure? We can we use another interrupt structure for this question? What do you think? Besides the external interrupt, can we use another interrupt structure? Of course, we can use another interrupt structure. For what? For timer, right? For timer, because for this question we use also timer to check 50 milliseconds. So if you do a setting for 50 milliseconds and if you exceed 50 millisecond value, you can easily understand this box can be class A or class B. Okay. Here the counting register is cleared. Uh, Set bit x1 enable external one. Set bit IT1 it's me falling edge triggered, and set bit enable all. The using pin will be cleared, and set bit TR1. Set bit TR1 it's mean timer 1 is enabled, and here we have an initial values for 50 millisecond. It's mean if we have uh, an overflow, it's mean exceed the 50 millisecond value, right? Okay, so after this condition, we are in this line endless loop. When the box is passed from under the sensor, program will go to the interrupt 1, as you see. Sorry, we didn't load the initial values to the counting register. We load the initial value for another register, which is 40 hex and 41 hex, to do some mathematical operation. Yes. When we go to the interrupt structure, first of all, we have to get TL1 because it can be changed. So first of all, the low byte or the counting register will be obtained to the 42 hex or another address. It's not important here. And TH1 is loaded to the A because we will do the first operation with TH1. The counting register will be cleared because we have already stored this value to the another register, which is A and 42 hex. Okay. and we store these values and clear the counting register because the new bugs can be came. Here we used compare jump if not equal. This code have another property. Let's examine it now. Yes, here. Compare jump if not equal. A and 40 hex, for example, will compare. But also care flag will affect from this can be affect from this comment. How? If 40 hex value is greater than A, care flag will 1. Otherwise, care flag will 0. So we can easily understand this. A is greater than 40 hex or not. Okay? We can use subcomment, but also we can use compare jump if not equal, and we can easily understand it is greater than or less than or not. Actually, this comparing will done on the background A minus 40 hex, and if the result is 0, program compare jump if not equal, program will continue, and if the result is not 0, program will go to the go label. We will solve this question by using this property. Let's continue. Compare jump if not equal A and 41 hex. What we have for the 41 hex here, VP high. This is the high byte of the 50 milliseconds. Okay. And if these are not equal to each other, we will continue from X1 label. What is X1 here? As you see here, care flag will check. Otherwise, if these values are equal, it means high byte of the counting register and 50 milliseconds are equal. So we have to check also low byte, right? For this, low byte will obtain to the A because here low byte will obtain to the 42 hex for A, and then yes, here we have a wrong. It should be 40 hex. Yes, we get the low byte of the counting register and then compared it with the 40 hex, which is low byte of the 50 milliseconds. And if these are not equal, we'll go to the X1 and we will check the care flag. Or if this value, it is wrong, yes. If this value are equal to each other, it means this box will class A because exactly 50 milliseconds. Okay, so we can easily do it class A. As you see, if it is class A, we will send a positive pulse. Let me continue. If these values are not equal to each other, we will go to the X1 label. X1 label, we will check the care flag. If care flag is 1, it means A is less than 41 hex. Sorry, the value in 41 hex, which is high byte of the 50 millisecond. In this condition, we'll go to the class A. So this label is class A, as you see. If it is, if we don't have carry, it means A is greater than, sorry, A is greater than 41 hex, exceed the value it means, So it means class B for us, set bit port 2.1 and clear port 2.1, as I remembered. Yes, over the 50 milliseconds, we set the port 2.1. I think we have a lack of program comment. What do you think? Can you see it or not? Okay, we have to check also TF1. Why? Because exceed the total machine cycle, right? So I think here we have to check TF1. Jump bit TF1. If it is exceed, it will send to the this label y class B directly. But if it is 1, we have to clear it. Clear TF1. I think it is uh, convenient now. Yes, if we use here line 24, we don't need to write this comment also in this label. Okay.